this. The balloon is held at a constant 23 degrees, so a constant temperature, as an addition of 2.5 moles of helium gas is added. What is the final volume of the weathered balloon if the pressure inside remains the same? So I'll give you a minute to just kind of think through this. A few things to note is that in the problem it says a constant 23 degrees Celsius. So anytime it says it's constant, we are going to cross off that variable from our equation like we saw yesterday. So also here we say pressure inside remains the same. So our pressure, this is also going to be constant throughout this process. So once again, we're going to begin with PV equals nRT, the ideal gas law. And then we're going to use the information in the problem that's given to work through the PV nRT. Let's see, number 2, I will just write down the equation for number 2 as well. And then I will give you some time to work on numbers 1 and 2 on your own. What questions do you guys have before I let you guys work? All right, so I'll mute my mic. Feel free to just ping me with a question whenever you get one, and then we'll come back together in a few minutes.
So when it says 1.5 grams of helium, I know we have to convert that into moles. Do I use 2 times the atomic mass to get the molar mass?
Good question, Kristen. Helium is not one of the diatomic molecules, so we're just going to use the regular molar mass from the periodic table.
Okay. Okay, thank you.
Good question. All right, let's start working on these together. If you didn't finish, that's completely fine. So yesterday we spoke about there being two types of problems where you're using the gas equation. One is a process, and two is a single state, right? Single state. So a process, it would be going from like initial to a final state. And the single state is just, it is what it is. You're just trying to find some property about that single state system. So number one, is number one a process or a single state problem? So number one is a process. So why is it a process? Well, we're starting out as some initial, so that I, and we're going to some final state. So the initial state was when we have 22 liters and 1.5 grams. And then in here, we're adding helium. And we're going to our final state, which has a different volume and a different amount of helium in it. So in this case, the process is, this is when we do the canceling. This is when we're going to do the canceling of variables that are constant. So in this problem, we're told that the temperature is held constant. So we're going to cancel out the T. And we're also told the pressure remains the same. In other words, the pressure is constant through the process. So pressure cancels. And the other one we can always cancel is the R. The R is just a number, and so therefore it's always constant. So we are given here that V is equal to N. Now the next step is to bring all of the variables onto one side. So in this case, we want to divide the N over to the left. So we get V divided by N is equal to something. Now, once you get all of the variables onto one side, this is where we copy everything. So take everything on the left and copy it onto the right. So V over N equals V over N. And what this signifies is the initial states and the final states, which we will write as 1 and 2. So 1 is the beginning and 2 is the end. Now let's put in the information we know. So we have the initial volume, we're told is 22 liters. And the initial moles. Just to remember, N means moles of gas, but we are given 1.5 grams of helium. So we cannot put grams in here. We need to convert this to moles. So up here, I'm going to convert 1.5 grams of helium into moles of helium. So moles of helium to grams of helium. So from the periodic table, 1 mole of helium has a molar mass of 4.0 grams. So doing this calculation, you should get the moles of helium is 0.375 moles. So we're going to put this in the 0.375 in for the moles initial. All right. Now the right side, we are looking for the volume. So the volume here is the variable that we're searching for. And state two has 2.5 moles of helium added. So this is going to be 2.5 moles plus the original amount. So 0.375. Now this is going to be the total moles at the end of this process. And from here, it's going to be an algebra problem So you're dividing on the left and then multiplying over. And if you have trouble with that, please let me know and we can discuss. And I get 168.6 liters. And I guess if we were doing sig figs, this would be 170 liters with 2 sig figs. What questions do you have on problem number 1? All right, let's work on number 2 then. So number 2 says a certain gas has a mass of 32.2 grams and occupies 5.6 liters at STP. So does anyone remember STP? What does this signify here?
Isn't it standard temperature and pressure?
Yes, it is. Very good. And so do you remember what the values for that is, Kristen?
1 ATM and 273 Kelvin.
Very good. Yes. So the temperature is 273 Kelvin, and then I butchered that. Pressure is 1 atmosphere. So ATM, we know the pressure, we know the temperature, and here we're told the we're told the volume. So V equals 5.6 liters. Okay, also we know the R value. Now the R value is always going to be the same, and that is going to be 0.08206. Now, I'll just remind you, we can always use this number as long as we're using liters, Kelvin, and atmospheres. Then you can always just put this R value in here. Now, the rest of the problem is saying, from the experiment, the gas is known to be of the noble gas group, which is the last on the periodic table. And so if that's the case, what is the identity of this element? So what we're going to want to do is if we can find the number of moles here, then we can use the grams and the moles to find the molar mass. And if we have the molar mass of this compound, we can very easily find its identity from the periodic table. So let's plug in the information we're given. So pressure, this is 1 atm. The volume was going to be 5.6 liters. The N, that's what we're going to be looking for, the number of moles in this container. The R, that's 0.08206. And then temperature is 273 Kelvin. So from here, we're going to want to do algebra and get the value for the N, which is the number of moles. And that's going to come out to 0.24997 moles. So this container has 0.24 moles of gas within it. Now, if we want to relate this to the periodic table, we're going to want to find the molar mass. So that's going to be a really easy way to figure out what gas this is. So molar mass is going to be equal to grams per mole, or grams divided by moles. Now, we know both grams and we know moles, which we just calculated. So the grams we were given in the problem is 32.8 grams. That was given here in the problem. And the number of moles, we know what that is. That is 0.24997. So do 32 divided by 0.24, and we get, this comes out to be 131.21 grams per mole. So we have one piece of information here, which is molar mass. And then the other piece of information we were given was it's in the noble gas group. So let's look at the periodic table and see the noble gas group, and we're going to look for a molar mass of 131. So the noble gas is this last column on the periodic table, all the way to the right. And if we look down here, this one right here, xenon, has a molar mass of 131. So we are going to say that the element that is inside this container with a molar mass of 131 is xenon. So the answer to this problem is Xe. What questions do you have on either problems number 1 or problem number 2? All right, let's move on to number 3. So let's read through number 3 together and discuss the balanced equation, and then I'll give you some time to work on the calculations on your own. So number 3 says, sodium calcium hydride, which is CaH2, reacts with water to form hydrogen gas and calcium hydroxide. This reaction is sometimes used to inflate life rafts and weather balloons. So part A says, what is the balanced equation for this reaction? Now, I can't remember who asked yesterday's session if we were going to be always given the reactions, but this would be a case where you have to develop the chemical reaction on your own. So let's write down what we're given. We're given CaH2, and we're told this is a solid, and this is reacting. This reacts to form, wait, what is it reacting with? Oh, with water, yeah. What am I thinking? Plus H2O. It's going to be liquid. And we're going to form hydrogen gas, which is H2 gas, and calcium hydroxide. So Ca parentheses OH close parentheses 2. And this is going to be aqueous since we're reacting it with water. Now, to balance this, we are going to need, let's see here, we're going to need a 2 in front of the water. Do this in another color here. We need a 2 in front of the water and a 2 in front of the hydrogens. So here we have our chemical equation. We're having a solid calcium hydride mixing with water, and it's going to produce hydrogen gas and calcium hydroxide. Now, the information that we're really interested in is this hydrogen gas. Now, why are we specifically interested in this hydrogen gas, and why do we not really care about this one? So, well, maybe I should have read forward a little bit to what we're doing. So we are searching for how many grams of CH2 we need to inflate a life raft. Now, the part that's doing the inflation is going to be the hydrogen gas. It's going to be this one. It's not going to be the CaOH2. Now, why is it just the hydrogen? Well, because the hydrogen is the gas. Only the gas can be used in the gas equation. So right here, the state of matter for the hydrogen is gaseous. Therefore, that is the one that we're interested in. Of course, this chapter we're doing gas laws. So I will let you work through part B a little bit, and we'll come back together in a minute and discuss how you would go about this. So maybe you've had a minute to just think through strategies for this one. So is there anyone that would like to share what they think they would do to solve this problem? Well, let me share then what I would do. So we are trying to find how many grams of CH2 is needed to inflate the life raft. Well, we know that it's going to be the gas that's doing the inflation. So we're gonna, whenever you hear gas, pretty safe starting out with PV and RT. Well, let's see, what do we have? We know the pressure. We are told the pressure here. We know the volume, although it's in cubic meters, not liters. So we'll have to do that conversion, but we have volume. We have R, we always know R, and we know the temperature. So we know everything here except moles. Now, why would moles be helpful to us? Does anyone know why, if we can solve for moles, anyone see why we would want to find N here?
Because we can convert moles to grams.
Right, exactly. Good job, Kristen. So if we can find moles, this is going to be moles of H2. And if we have moles of H2, we can convert back to calcium hydride and to figure out how many grams there are. So that is the approach we're going to want to use. So solve for moles of H2. Now let me give you a couple conversions here to use. The first one is that 1 cubic meter is equal to 1,000 liters. And the second conversion you'll need is that 1 ATM is equal to 760 torr. So make sure you convert your temperature to Kelvin, your cubic meter to liter, and then your pressure to atmospheres. And then why don't we give 2 or 3 minutes and try to work through this before we come back together. Are there any other questions on the problem setup? All right, let's continue working on this one together. If I'm going too fast or too slow, just let me know in the chat. Sometimes it's hard to gauge over when it's virtual. So let's convert our 4.37 cubic meters into liters. So we are told that 1 cubic meter is going to be 1,000 liters. So that one's pretty easy, 4,370 liters. For the ATM to torr, I'm going to erase that. We do same thing, so 825 torr, and so 1 atmosphere is going to be equal to 760 torr. And I put torr on the bottom so that it cancels 1 unit on top, 1 unit on bottom. And this comes out to be, let's see here, 1.086 ATM. And then for temperature, we're going to be temperature is going to be equal to 27 plus 273. So that's going to be, I think, a nice round 300 Kelvin. Okay, so we got our correct units, and now we're going to put this into our PV nRT equation. So pressure 1.086 ATM times volume, which is 4,370 liters. We don't know number of moles, but the R value we do know. That's 0.08206. And the units, if you're interested, is liter times atmosphere divided by moles times Kelvin. But as long as you have the other units correct, you will be fine. And
wait, where does the R come from again?
Good question. I didn't see who asked that. So the R value is a what's called a constant, or the ideal gas constant, and it relates all of the units together. So it relates atmospheres, liters, Kelvin, and moles. Now it's called a universal gas constant because it's universal for all gases. And this value here you can find in textbooks. There's different values depending on different units you use, which makes sense. So this links together all of your units. So for example, if you put in like temperature here if you put in Fahrenheit, that wouldn't make sense in this. So you would have to use a different N value. So I guess my explanation is it's kind of like the chain link that links all of your units together. And for our units in this class, it's always going to be the same number, 0.082. Does that answer your question, or is that so confusing?
No, that's good. Thank you.
Okay, sure thing. So solving for N, we get, let's see, I got 192.78 moles of gas. Now, in this case, what is it moles of? Well, it's going to be moles of hydrogen. Why is it moles of hydrogen? Because in our balanced equation, the one that is the gas is the hydrogen. So it's not going to be CaOH2 because that one's aqueous. So all of this volume, this 4,300 liters of volume, is going to be all made up, or almost all made up, of the hydrogen. So now we want to convert into grams. So we have, let's see, 192.78 moles of hydrogen gas. And we want to convert to grams of CaH2. So we're going to get rid of moles of hydrogen, and we're going to go to moles of CaH2. So the conversion between moles and moles for here is going to be 2 to 1. And once again, that is the coefficients from the balanced equation up here. So we have a 2 and 1. And then the next thing we want to do is go to grams. So mole CaH2 and grams CaH2. So we have 1 mole of CaH2, and the molar mass of this compound is 42.10 grams per mole. So let's make sure our units cancel here. We have mole H2 cancels, mole CaH2 cancels, and we're left with grams of CaH2. And for this one, I got a final answer of 4,058.02 grams. And if we were doing sig figs, the problem started with 3 sig figs. So this would be 4,060 grams of CaH2. What questions do you have on this problem?
So how do you know it was gram or moles of H2 that we got?
Good question, Kristen. Does anyone else know why this was moles of H2 specifically?
Wasn't it because of the gas? Like, it's
Yes.
the only gas?
Yes, exactly. So technically this is moles of gas. It's moles of gas because we're doing gas laws. PV-nRT is a gas law. So the N is always going to be in moles of gas. Now the question here is, what in our problem, which substance is gas? Well, it says up here in the problem that it forms hydrogen gas. Therefore, this is going to be moles of hydrogen. Does that make sense?
Yeah, it does. Thanks.
Okay, great. All right, let's move on. I know today's kind of a big calculation day. So why don't we pass on from number 4. We'll do number 4 maybe on Monday, just because I don't want to throw another big calculation at you. And let's discuss the next topic for chapter 5, which is gas density. So for gas density, there is a specific equation. Does anyone know what the equation for gas density is? All right, so the equation for gas density is going to be equal to D is equal to pressure times molar mass divided by the R ideal gas constant times temperature. So let's type out, maybe I can just type here, what each of those stands for. So D is going to be equal to the density of the gas, which density in this class is going to be measured in grams per liter. So how many grams of gas are there in a 1 liter volume? The P is going to still be pressure, and this is in atmospheres. MM, this is going to be the molar mass, and we know the units of that is grams per mole. R, this is still going to be the ideal gas constant. And this is going to be 0.08206 liters atmosphere per mole Kelvin. Once again, you don't really need to know the units as long as you're using liters, atmospheres, and Kelvin. And then lastly, T, this is going to be temperature, and we have to use Kelvin as well. What questions do you have about the equation for gas density?
No cap, but I kind of missed like half of this part. Like, I'm
Yeah.
so sorry.
No, that's okay.
Where did that D come from?
So the D is density. Is that what you're asking here?
Yeah. Mm-hmm.
Yep. So this we're kind of getting away from the PV-nRT and we're moving into gas density. This is another one of the gas equations here. And what's nice about this one is more or less plug and chug. So why don't we spend, I'll give you a couple minutes to try to work on part 6. And part 6, we are just applying the equation. So try to take a few minutes and work on 6 and let me know what questions you get. All right, let's do this one together. So pressure. Yeah, okay, so pressure. We are given in this problem, we are told it is STP. So that means 1 atmosphere for pressure. For molar mass, so molar mass in this case is not directly given, but we can find CH4 from the periodic table. And let's see, that would be 16.04 grams per mole. So 16.04 grams per mole. The R value, this is always going to be the same, 0.08206. And then the temperature, once again, this is given, it's hidden in the STP. So STP means 273 Kelvin. So from here, you're just grabbing your calculator and punching it out, and you should get 0.716 grams per liter. So that would be your answer. Now the problem also mentions you can, to convert this to kilograms per cubic meter. So this is another common unit that's used, kilograms per cubic meter. So if we were going to convert grams to liters, we would do this conversion. So put grams on bottom, so it cancels, go to kilograms. So 1,000 grams is 1 kilogram. And then to convert to liters to meters cubed, so 1,000 liters is 1 cubic meter. So essentially here you're just dividing and multiplying by 1,000. So this actually comes out to be the same. Fun fact. So same thing, 0.716 kilograms per cubic meter is the gas density. So gas density, not too difficult. Most of the problems are going to be just like this. What questions do you have on gas density or on anything else for the worksheet today? All right, we will stop there for today. Hope you guys have a good weekend, and we'll see you on Monday.